We had 2 bits of homework last night that we're going to check over today. The first set was page 810, number 1, 3 to 7, 9, and 11. Any issues with those questions on page 810, please? Courtney? 12C? Oh, yeah, you're right. We didn't have to do 12. 6? 6? 11C? 9? We got 6, 9, we got 11C, going once, going twice. All right, let's take a look at 6 here. Number 6 says, explain why the daughter nucleus in an alpha decay often emits a gamma ray. Can anybody give me an answer to that question? How did we say gamma rays were produced? In general, we say by nuclear decay, right? That's what we said last unit, but we talked about that a little bit more specifically this unit when we talked about alpha, beta, and gamma decay. Alpha decay occurs when you get too many protons. Beta minus occurs when you've got too many neutrons. Beta plus occurs, again, when you get too many protons. Gamma occurs, yes, when the nucleus is left in an excited state. So why does it sometimes occur after an alpha decay? Well, because after an alpha decay, the nucleus is left in an excited state. As it goes back down to its normal state, it gives off energy, the energy that it had when it was excited. That energy is going to be in the form of a gamma ray. Number 9. It says, explain whether the atomic number can increase during nuclear decay, and explain or support your answer with an example. Can the atomic number increase during nuclear decay? The atomic number is the number of protons. If the atomic number changes, then clearly the type of atom or the type of nucleus changes. Is that possible? Yes. Cole says yes. That's nuclear physics, right? That's what happens all the time in these transmutation equations, is that the nucleus changes into something else. The atomic number changes. But can the atomic number increase? Can the atomic number go up? In most of the questions we do, most or all of them, the atomic number goes down. Is it possible for it to go up? And if it is, in what situation is it possible to go up? Beta minus decay, good. When you have beta minus decay, for example, you have beta minus decay, it looks something like this, maybe carbon 14. That's certainly the most common beta minus decay, or at least it's the one that most people know. It's the one that always comes to my mind when I think of beta minus decay. 14,6 carbon goes to 0, minus 1 beta plus, well, 0 plus 14 is 14, minus 1 plus 7 is 6, and that's going to be nitrogen. So in that case, obviously, the atomic number has increased. It decreases all the time. In beta minus decay, well, it increases. Finally, we had one more question there to go over. It was question 11C. I remember that one, actually. That one looks a little bit odd, right? It says radium-228 goes to radium-228. What type of decay is this? If I redrew this like this, would that make a little bit more sense to you? That's gamma decay. What happens here? If we take a look at A, we've got alpha decay occurring, right? Thorium-232 decays into radium-228 plus an alpha particle. What happens to the radium-228? It's left in an excited state. As it goes back down to its normal state, it gives off a gamma ray photon. It doesn't change the atomic number. It doesn't change the mass number, because a gamma ray has 0 protons and 0 neutrons. So that's what we got there, is gamma decay, simply because this radium-228 is left in an excited state as a result of alpha decay, in this case. Good? All right, your other bit of homework that you had last night was page 817, questions 1 and 3 to 9. I suspect we had probably a few issues with this page, page 817. Brenda? 6, 7, 8, yeah. 6, 7, 8, 9. 6, 7, 8, 9. All right. Let's take a look at number 6 here. Question 6 says, an archaeologist finds a wooden arrow shaft with a proportion of carbon-14 that is about 25% of that in a living tree branch. Estimate the age of the arrow. Or at least, really what we're finding here is how long it's been since that branch was cut off the tree to make the arrow, right? Since the wood became a non-living thing. We know the half-life of carbon-14. I mentioned yesterday when we did an example, remember to go back to this example to find the half-life of carbon-14 because you're going to use it again. It's 5,730 years. If you get this question on the exam, that information will be given to you somewhere, buried probably in 3/4 of a page of information, but the half-life will be given to you. So the half-life is 5,730 years. We're looking for the age of the arrow. We're looking for the time that it took to decay to 25% of what it was. Do we know what the value of n sub 0 is? The original amount here. Since we're dealing with a percent, we're almost always going to make n0 what? 100%. That's going to make n, the final amount, 25%. Let's use my equation. N is equal to n sub 0, 1/2 to the little n. That's going to be 100. We're going to say 25 is equal to 100, 1/2 to the little n. We've got to solve for a little n here. We've got a couple of ways of doing that. We can use the divide by 2 method, or we can use the logarithm method. Here's the divide by 2 method. After 0 half-lives, we've got 100%. After 1 half-life, we've got 100 divided by 2 is 50. After 2 half-lives, we've got what? 25%. So we can say that n is equal to 2 without doing anything with that equation per se, simply by dividing by 2. Once we recognize n is equal to 2, well, then we can say n is equal to t over t 1/2, or t is equal to n times t 1/2. It's 2 times 5730, which is, what is that going to be, 11,460? Is that right? 5730 times 2? Now, the other way to find little n is to use that equation. Let's use logarithms to do that for those of you who are comfortable with logarithms. We're going to say n is equal to log n over n sub 0 over log of 1/2, or of 0.5. If you're not comfortable with logarithms, then don't do this. If you've never done logarithms before in your life, then don't even pay attention to what I'm doing right now. Just use the divide by 2 method. And so we say log of 25 over 100 divided by log of 0.5, and when we do that, we should still get 2.0, which we turn around and plug into here, giving us still 11,460 years. How many people, when they did this question, used the divide by 2 method? How many people used the log method? Okay, more people using the log method. That's the benefit of having Physics 30 second semester. One small benefit of having it second semester is that most of you at this point will have done logarithms. In first semester, it's probably less than 50% have done logarithms, because a lot of people take in Math 30 in second semester. Okay, number 7 says a radioactive sample has an activity of 2.5, what is this, MBQ, and a half-life of 12 hours. This is an activity, this is an amount of decays that are taking place. In fact, an MBQ is a mega, a BQ is called a becquerel. It's a decay per second. Although that doesn't really matter, to be honest. 2.5 million decays per second. That's what that means. But again, it's not really a big deal if you understand what that BQ means. The important thing is you recognize that that's the activity, that's an amount. So N, for that question, let's get rid of some writing here. So N would be 2.5 MBQ. Remember, we can use whatever units we want for N, as long as we use the same units for N0. Sorry, that's going to be N0, right? Because we were looking for the activity a week later. So this is what we start with, is 2.5. What do we have a week later? The half-life is 12 hours. The time is 1 week. Well, we want to convert that week to hours, or we can convert the hours to weeks. It might actually be a little bit easier this time to go the other way around and convert the hours to weeks. 24 hours would be 1/7 of a week. 12 hours would be 1/14 of a week. Now, it doesn't matter. You want to leave it in hours and then multiply the number of weeks by 24, by 7 to get the number of days, and then by 24 to get the number of hours. Go ahead and do that. You're going to get the same answer in the end here. N is equal to n sub 0, 1/2 to the little n. We've got to find the little n by saying t over t 1/2. That's going to be 1 over 14 divided by 1. Nope, the other way around, isn't it? It's going to be 1 over 14, which is the same as saying 1 times 14 over 1. Little n is going to be 14. Well, let's say now it's 2.5 megabecquerel times 1/2 to the 14. What do we get for that when we do that math? Somebody have that already? Nick, you got that? 1.53 times 10 to the minus 4. Anybody else get that? Now, that's a really small number compared to the 2.5, right? But it seems reasonable to me. Yeah, I don't know if it's right. I trust you because a few people say that it is. But it seems reasonable to me because, look, it's 14 half-lives. That's a lot of half-lives. That's a lot of dividing by 2. So in the end, 1.53 times 10 to the negative 4 seems entirely reasonable. Look, you read this question, you see this MBQ. Don't worry about that. If it's a unit you don't recognize and it's a half-life problem, you know it's not time. Or you know it's not t. So if it's not t, then it's probably going to be either n or n sub 0. Courtney, is there a question with this or a mistake that we've made?
No, I don't think I got like 7 over 6.
7 over 6 for n?
Yeah, because, well, I think I thought about it wrong, but I said that like the half-life is 12, and then there's 14 12-hour periods.
Yeah. Yeah.
Then I just did 14.
Oh, 14 over 12. Oh, yeah. Yeah. No. Your logic in that is wrong. Yeah. Because it's got to be the total time divided by the half-life. Your total time isn't 14, right? So you said 14 divided by 12. Well, the half-life is 12 hours, but the total time isn't 14 hours, right? And that's what you effectively did. Yeah, if you did it in hours, you got to find the number of hours in a week, right? 7 days times 24 hours. Sorry, times. Yeah, it's going to be 1 week times 7 days times 24 hours gives me whatever number of hours. Yeah, and you're still going to get 14. You did what? 168 hours? Okay, now let's go 168 hours divided by 12. And what do you get? What'd you get for little n? Okay, so we've got, so you did it using hours, I did it using days. We both got 14 for little n. Let's just plug that number in now. 2.5 times 0.5 to the 14 gives me 1.525, which rounds to 1.53. Yeah. Okay. Next question we got to look at is 8 and 9. Question number 8 says, graph the data in this table, then use your graph to estimate the half-life of the material and the activity of the sample at t is equal to 0 seconds. I'm not going to actually plot this graph on GraphPaper because I don't have any in front of me right now, but the graph is going to look something like this. The activity is going to be on the y-axis, second column of my graph, of my table, right? So it's on the y-axis, and that's going to be in decays per minute. And my time in hours is going to be on my x-axis. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're going to go from 0 all the way up to about 3,000. My graph, when I plot it, should look something like this, if you use graph paper and if you plot it to scale. Now, you want to find the half-life? It's probably easiest to actually find the activity at time is equal to 0 first. How do we do that? Because we don't really have a y-intercept per se on this graph. Let's extrapolate. Let's go back here. Okay, let's extrapolate this graph and see where it goes through the y-axis. That will be n sub 0. That will be the initial amount, the activity at t is equal to 0. Now, I don't know what that value is, because I don't have a graph that's plotted to scale here. But you can easily read that off your graph if you've done that to scale. Now, how do you find the half-life? Question A. The half-life of the material? Well, let's go halfway down. If my original amount was, say, 3,500, which I'm going to estimate that it was somewhere in that range, 3,500, 3,800, somewhere in there. Well, then let's go down to 1,750. Let's go down to half of it, half of what I started with. Now let's go over and down. When we go over and down, we read the time. That time will correspond to the half-life. Now again, because I don't have a graph that's plotted to scale, I don't even want to begin to try to tell you what the half-life is there from that graph. But that's exactly the way we do it. You mean for B? No, I wouldn't guess. I wouldn't call it a guess. But it's extrapolating the graph so that you're going to take an approximate number from the y-axis as you extrapolate it through the y-axis. Mathematically? Well, the problem is, if you try doing it mathematically, you've got a whole bunch of data points. Right? So what data point do you pick? The whole issue with not using an equation with a particular data point is that what if that data point is off? Right? A graph kind of accounts for that for us, right? You know, we've got a graph that looks like this, but we've got some data points kind of like this. What if we pick this data point? It doesn't fall on the line. So we're best off to use that line. Hour 8 is half of hour 4. Actually, that's a good idea. Actually, it's a good idea. But you still run into that issue of using particular data points with that. Okay. The point up here was just made that hour 8 is 900. Hour 4 is 1800. So the half-life should be 4 hours, right? Because it took 4 hours to decrease that to that. And that's a good idea. But again, and that will probably work here, but the problem with that potentially is that using data points as opposed to using a graph, what if one of those data points is off? And what if this should be really 19 and this should be 800? Okay, make sense? It's a good idea, and it probably will work, but we're not guaranteed of that. Yep. Yeah, no, I think that would be relatively safe to say, yeah, if you had a bunch that did the same thing. Do we here? Close, yeah. Oh, is it exact? Okay. So that's, yeah, it's probably exact data that they're giving us there then. Drew? Okay, so you're using the equation logarithms, right? You're using n is equal to n sub 0, 1/2 to the little n, and solving for a little n using logarithms there between data points 1 and 2. Again, okay, your idea is good. Your idea, Joel, good. Okay, Drew, your idea is good too. You can use that. But the issue with all three of those, again, is you're using data points. You're using this and this. What about all the rest of them? The graph takes into account all of the data points as opposed to one or two data points or two different data points or two different data points. Okay, does that make sense? So it's always better if you have a graph to use the graph because it kind of accommodates for slight errors in measurement, even if sometimes they're not always there. They won't make you graph on the diploma because it's multiple choice and numeric response, right? But they will make you interpret a graph. Now, when they make you interpret a graph, they could make you interpret something like this, but they will make you interpret a straight line graph. Okay. Now, whether it's a straight line graph that we've done before or not, that's, all bets are off on that one. But that's okay because we've learned how to deal with that, right? They may make you do something like this as well, but they'll never make you plot one because, how do you plot one with multiple choice? It's multiple choice, right? All right, number 9. A dealer in antiquities offers to sell you an authentic dinosaur bone for a mere $100. He shows you a certificate indicating the carbon-14 dating determined that the bone is 65 million years old. Why should you be suspicious? We kind of alluded to this a little bit yesterday. Why should you be suspicious, Drew?
The half-life of carbon-14 is 5,730 years.
Yep.
So it's 5 million years old. Carbon-14.
Yes. Yes. You remember we said when we started this whole thing about radioactivity yesterday that this only works. These calculations are only approximations because we don't know exactly what's going to happen. It's just based on past performance, right? Past history. But it works very well when you have a big sample size. You flip 1,000 coins, odds are you're going to have pretty darn close to 500 heads. 50-50, right? You flip 2 coins, all bets are off. You could have half and half. You could have all heads, or you could have all tails. When you're dealing with a big sample size with radioactivity, same thing applies. Okay, the statistics work. But when you're dealing with a small sample size, the statistics might work, they might not work. It's just, you can't put any faith in it when you're dealing with a small sample size. And as Drew said, because the half-life is 5,730 years, look, it's millions of years old, 65 million years old. That's so many half-lives that have gone by. The amount of carbon-14 that you would have left in there is so small, so tiny, that it's too small of a sample size to rely on our calculations. You've got to have a big sample size to rely on those calculations, and you wouldn't have enough there. Okay, does that make sense? All right, I was going to spend a few minutes reviewing the whole radioactivity thing, but I think the questions that we've gone over here today, I think will kind of account for that. I think we've gone over a good kind of sample of different questions that we'd pretty much be going over as we were reviewing our stuff. So I think what we're going to do here is move on. What I will do, before we move on actually, is assign worksheet number 25 on radioactivity. We're not going to work on that right now, but you may very well have a little bit of time to work on that down the road in today's class. I would like you to work on this question right now, though. We'll give you a minute or two to see what you can do with this question, question 162 in your worksheet booklet. All right, let's take a look at this question now. It says, in medical diagnosis, a patient may be injected with a radioactive isotope. As the isotope decays, the gamma ray emissions are detected, and a computer builds images of a patient's blood flow and organs. A radioactive isotope commonly used in medical diagnosis is technetium 99. The isotope has a half-life of 6 hours and decays to a stable isotope by gamma ray emission. This is our half-life here, and looks like that's all we have, isn't it? At least up there. The question says, if the biological processes that might eliminate some of the technetium-99 from the body are ignored, the maximum percentage of radioactive technetium-99 that could still be present in a patient's system 24 hours after injection, that's going to be T, is what? What's N sub 0 going to be? If all of my answers are in percents here, then what are we going to make N sub 0? Let's make N sub 0 100%. Let's find N. It's N sub 0 1/2 to the little n. Little n is going to be T over T 1/2. That's going to be 24 divided by 6. Little n is going to be equal to 4. We don't have to use logarithms here. We don't have to use the divide by 2 method. Okay, let's simply divide T by the half-life. Now let's say 100 times 1/2 to the 4. That's going to give me 50, 25, 12.5, 6.25. Is the answer B? It's good. How many people got B? Okay, good. One more of these multiple choice questions, please. Number 163. Give you a minute to work on that one. Let's take a look at 163 now. Americanium-243. This information we've seen before, right? This whole smoke detector thing. At the end, the 9-volt battery isn't going to be really relevant. The only part that's going to be really relevant to this question is the stem of the question. Americanium-243 has a half-life of approximately 7,000 years. Let's call that T1/2. A detector containing 20 milligrams of this isotope were discarded. That's going to be our initial amount. We're recovered 70 years later. That's going to be T. How much would remain? So we're looking for N here. We're going to say N is equal to N sub 0, the initial amount, times 1/2 to the little n. That's the number of half-lives. Little n is going to be T over T1/2. Now, this is going to be a pretty small number. T is 70 years. T1/2 is 7,000 years. What's 70 divided by 7,000? 0.01, right? Let's say N sub 0, 20 milligrams again. We're in milligrams. It's a strange set of units, but it doesn't matter. As long as we're consistent here, we can use whatever units we want. 20 milligrams times 1/2 to the 0.01. What do we get when we do that? 19.8. Approximately, how much is going to remain? 20 milligrams, right? Listen, when I looked at that question, I knew the answer to that question right away. And I knew the answer to that question right away, and I suspect a number of the rest of you did as well for the same reason as I did. 7,000 years is the half-life. We've only gone through 70 years, a tiny portion of that half-life. You're going to lose hardly nothing, right? Here we're losing most of it. Here we're losing the vast, vast majority of it, and here we're losing all of it. So the answer's got to be A. All right. Today we're going to talk about two other nuclear processes. Today we're going to talk about nuclear fission and nuclear fusion. Nuclear fission is a process in which one heavy nucleus splits apart into two or more lighter nuclei. So we're going to say heavy nucleus splits up into lighter nuclei. There's lots of examples of heavy nuclei splitting up into lighter nuclei. Lots of examples of nuclear fission. The one that you see up on the board is one of them. The picture that you see up on the board has two bombs in it. This one, the Americans nicknamed Fat Boy. And this one they nicknamed Little Boy. Fat Boy was the bomb that was dropped on Nagasaki in 1945. Little Boy was the bomb that was dropped on Hiroshima in 1945. Little Boy was a Uranium-235 bomb. Fat Boy was a plutonium, I think, what's plutonium? P-U? P-T? Okay. Somebody check your periodic table for that. Plutonium, yeah. I think it might be Pu. Pu. Yeah, I thought it was. Plutonium-239. Now, the Uranium-235 bomb, it's kind of interesting. The first one that was actually dropped on Hiroshima, it was about 16 kiloton bomb. A 16 kiloton bomb has the energy equivalent of 16,000 tons of TNT. That's about 50,000 sticks of dynamite. So the bomb that was dropped on Hiroshima had the equivalent of about 50,000 sticks of dynamite. The bomb that was dropped on Nagasaki had about 21 kilotons, so about 21,000 tons, the equivalent of 21,000 tons of TNT, which is somewhere in the range of 75,000 sticks of dynamite. That's a lot of energy. But the bombs we have now, or at least the bombs the Americans and nuclear powers have now, make these ones pale in comparison. Now we're dealing with megatons of TNT as opposed to 21 kilotons of TNT. So this is an example of a nuclear fission reaction. One example, uranium-235. This would be a uranium-235 fission reaction. In this case, you can see that uranium, the one heavy nucleus, is splitting up into krypton and barium, two lighter nuclei. Now, understand that uranium-235 will decay on its own eventually, but we don't want to wait for that to happen in the case of nuclear fission. So we prompt it to happen. We kind of kickstart it. We do something to kind of make it happen. It's kind of like you see that big block of ice and you're a little kid and you're waiting for that big block of ice. You can tell it's ready to break apart, but it's not quite breaking apart. You want it to break apart quicker, so what do? You take a hammer to it and you hit it. What happens now? The block of ice breaks apart. We're taking our hammer or our neutron and smashing it into the uranium-235. It actually briefly fuses with uranium-235, becomes uranium-236, and then that causes it to become unstable, splits up into krypton-92 and barium-141. It also gives off some extra neutrons, and it gives off some energy as well. Now, how does this create the equivalent of 16 kilotons of dynamite or 16 kilotons of TNT? This is 200 mega electron volts. That doesn't seem like a lot of energy, and in fact, it's not a lot of energy. It's about enough energy to move maybe a speck of dust. We don't blow up a city by moving a speck of dust. We blow up a city by moving lots of specks of dust. But we can't keep firing that many neutrons at this uranium-235 that many times to move that many specks of dust. So what we do in the case of a nuclear weapon is try to create what we call a chain reaction. A chain reaction exists when the products of one reaction become reactants for the next reaction. In other words, these three neutrons will hit three more uranium-235 nuclei, which will cause 600 mega electron volts now, because we got three more reactions taking place. Well, that produces 9 neutrons. Those 9 neutrons cause 9 more reactions in the energy that goes with that. Those 9 more reactions will produce 27 neutrons, and then 27 more neutrons, or 27 more reactions, and then 81, and then 243, and so on, and so on. So that you can see within a very, very short period of time, we're talking about a fraction of a second here, the energy has grown exponentially so that we're releasing 21, or 16 in the case of the uranium-235, 16 kilotons of TNT energy. Okay, this all happens within a very small fraction of a second. Now, what's kind of interesting here is that this little boy here, this little boy bomb that was dropped on Hiroshima in 1945, had only 64 kilograms of uranium present in it. Uranium is our fuel, right? It only had 64 kilograms of uranium present in that bomb, and that blew up a city. What's even more interesting is that the energy that comes from this comes from converting mass to that energy. And the amount of mass that was actually converted to energy was only about 700 milligrams of mass. 700 milligrams of mass. Less than 1 kilogram of mass destroyed a city and killed tens of thousands of people. Okay, why does it do that? Well, you learned this earlier on in this in our last unit. Energy is equal to mc squared. If you have 600 or 700 milligrams of mass converted to energy, that ends up being a lot of energy. Okay, does that make some sense? Fission is the process whereby the heavy nucleus splits up into a lighter nuclei. Look, there's a lot of stuff around this. Neutron here, neutrons here, energy here. In the end, you want to identify whether it's fission or some other reaction. Look at this. Look at the big nuclei. Okay, one big one is breaking apart into two smaller ones. Forget about the neutrons. Okay, one big nucleus splits apart into krypton and barium, two smaller nuclei. The neutrons that occur as a byproduct of that reaction cause more reactions, which create this chain reaction. Now, if we've got a nuclear power plant, we don't want this uncontrolled chain reaction, right? We don't want it to grow exponentially because we don't want to blow things up. So what do? Well, we have these control rods to absorb extra neutrons. You get too many neutrons being produced, it's getting a little bit too warm, too many neutrons produced, let's absorb some of those neutrons. Let's not let some of these extra neutrons react with more uranium. Okay, we want to speed the reaction up a little bit, let's take some of these control rods out. Not enough reaction is taking place. Let's take some out. Let's allow a few more neutrons to react with the uranium-235. Oh, it's slowing down again, or it's speeding up again. It's getting a little bit too fast. Too much reaction is taking place. Let's put some more control rods back in to absorb more uranium-235. So in a bomb, we want the chain reaction. In a power plant, obviously, we don't want this uncontrolled chain reaction. Now, this term mass defect. Mass defect can be defined in a couple of ways. The first way is the difference in mass. This is going to make sense when you first see it. Just bear with me for a second. The difference in mass between the nucleus and the nucleons. A nucleon, by the way, is a proton or a neutron. If you take protons and neutrons and you put them together and you make a nucleus, the nucleus oddly weighs less than the protons and neutrons weigh. When you put these protons and neutrons together, somehow the product of what you get, the nucleus, weighs less than the protons and neutrons weighed when you put them in. The difference in mass between the protons and neutrons and the nucleus itself is what we call the mass defect. I'm going to just put in brackets here. The nucleus weighs less. So you lose mass there when you put them together. The nucleus weighs less than the protons and neutrons combined, which is really, really odd. But it is what it is. Now, the other way we can define mass defect is the difference in mass between the products and reactants, or between the daughter nuclei and the parent nuclei. Now, it seems like two different definitions, but in the end, this second definition stems from the first definition. It's because of the first definition. That mass defect, the difference in mass between the products and the reactants, is what causes this energy to be released. That mass defect is converted to energy by the equation E equals mc squared and releases 200 megaelectron volts of energy. Nuclear fusion, on the other hand, is when we have two lighter nuclei combining to form one heavy. They fuse together to form one heavy nucleus. Now, there are lots of examples of nuclear fusion as well. This is one of them. Hydrogen-2, we call that heavy hydrogen. Normal hydrogen, the normal isotope of hydrogen would be hydrogen-1, is one proton, no neutrons. This is one proton and one neutron. It's heavy hydrogen. Chemically, it's identical to regular hydrogen. It can be in water. You can make water out of heavy hydrogen. We call it heavy water. Okay, H2 and H2 fuse together to form helium-3. They also kick off a neutron there, and it releases a bunch of energy. The problem with this one is making it happen. Hydrogen and hydrogen don't want to fuse together because they're both positive. There is a force of repulsion between those two positive charges. And that force of repulsion gets bigger as the distance between them gets smaller. So as these hydrogen get closer and closer and closer together, the force of repulsion gets bigger and bigger and bigger and bigger. We need to pump a whole lot of energy into this to make it happen. Usually that energy is in the form of heat. If it's really, really hot, these hydrogen nuclei can be energetic enough to overcome that force of repulsion and get close enough to fuse together. It happens in the sun all the time, right? The sun undergoes nuclear fusion all the time. That's our source of energy on Earth. That happens because the sun is hot. The heat from the sun allows more hydrogen to fuse together to overcome that repulsive force, form helium, and then produce a whole lot of energy. The bombs that we have now tend to be fusion bombs, and they end up releasing a lot more energy than the fission bombs. Again, we're in the order of megatons as opposed to barely double-digit kilotons. Now, kind of what's interesting about the first nuclear fusion bomb, called it the H bomb, which was this reaction right here, created in 1952 by the Americans 7 years after the end of the Second World War, is that in order to make this happen, in order to get these hydrogen to fuse together, they actually used a fission reaction. So they essentially exploded a nuclear fission bomb, essentially, just to kickstart this into motion, just to get this going. This becomes self-sustaining because some of this energy will cause more hydrogen to fuse together, and then so on and so on and so on. But you got to get it going somehow. Usually it's in the form of heat. Well, the sun's got its own heat, so it causes hydrogen to fuse together all the time. A fusion bomb, well, you need some source of heat. Let's make a fission bomb inside it. Now, we don't use this in nuclear power plants like we do nuclear fission. Why not? Right now, we have no way of controlling it. Okay, so basically, if we tried to build it, we'd be building a bomb. And that's not what we want when we're trying to generate electricity. Question? Okay. Good. Mass defect again, we already defined that. Defined it in two ways, in fact. We defined it as the difference in mass between the nucleus and the nucleons, the nucleus and what makes up the nucleus. Remember, the nucleus weighs less than the nucleons. We also define it as the difference in mass between the products and the reactants. The products weigh less than the reactants. Where's the mass gone? It's been converted to energy. So the two ways that we define the mass defect, and again, the second way that we defined it really is just because of the first way. Now, there's a number of ways to define binding energy as well, but we'll define it only in the way that we need to be able to solve what we need to solve. We're going to define it as the energy released in a nuclear reaction. You could define it as well as the energy that's required to build a nucleus. But that's not really a relevant thing for us. Okay, we care about it kind of the other way around. The energy that's released when you rip a nucleus apart. The energy that's released in a nuclear reaction. Now, define the binding energy, the energy that's released in the nuclear reaction. We're going to multiply mc squared, m being mass. What mass? What does m stand for here? The mass defect. the mass that disappears in the nuclear reaction, well, it wasn't just destroyed, it was converted to something. It was converted to energy by the equation E equals mc squared. Now, there's 3 units here. We're not going to spend a lot of time on these 3 units, but I want to briefly tell you what these mean. Okay? We look at these right away, these MeV, GeV per c squared, and we think energy, right? Electron volts, okay, energy. But remember, it's divided by c squared. So if you rearrange this, m is equal to E over c squared. These are actually units of mass.
Just a reminder that
As is this.
Today during worship.
This is what we call an atomic mass unit. It is 1/12 the mass of a carbon-12 atom. 1 atomic mass unit is equal to 1.66 times 10 to the minus 27 kilograms. And that conversion factor is on your data sheet. All right, we don't have time to do the example here today, but I think it's a pretty straightforward one, so I'd like you to try doing the problem that goes with it here. Page 794. There's a couple practice problems on 794. I think you should be able to finish those practice problems up literally within 1 to 2 minutes. Okay? You also have your worksheet number 25. That's going to take a little bit longer, but that's it, other than your little quiz tomorrow. All right, that's it for today.